who will be joining me on stage later to talk about their journey from batch to real-time processing. But first, a couple of key concepts to cover. First, we'll talk about the modern data landscape, what's changed, and what's made us look to make this transition from batch to streaming in the first place. Then we'll compare batch versus stream processing. We'll talk a little bit about some data architectures and some ingestion patterns. And then that hopefully will build a nice foundation and context for us to move into Mimecast's journey from batch to streaming. Then we'll do a quick recap, hopefully summarize some of the insights that we believe would be helpful to you. So let's talk a little bit about the modern data landscape. What's changed? We have data coming in from new and diverse sources. We all know the 3 V's or the 5 V's of big data: volume, variety, velocity. That's exploded even more and more now. So you have many data sources to deal with. They're not playing fair. They're not the same format. They're not the same speed. They're not the same anything, and you still need to get insights from them. But more and more, this data is being produced continuously. Before, you just had to deal with a schedule. Something is coming in once a day, maybe once an hour, that's all right. But now that you have data coming in all the time, you need different paradigms and different technology and different skill set, frankly, to be able to deal with that data and extract insights from it in a useful way. And finally, a lot more people have been greedy to get their hands on data, especially business teams. They now know that data is the new oil, right? And they're looking to even get self-service capabilities for them and eliminate the bottleneck from their perception of IT or from a data platform team so that they can actually produce the insights themselves. That means that you have a lot more downstream consumers for your application before. That includes people who are analyzing data, but it also includes applications, APIs, endpoints, data exchanges. The number of parties that are looking to make sense of the data that you were bringing in before has also increased. Not only that, we also realize that the value of data diminishes over time. With batch processing, we can only deal with data that is historical, that's been produced hours or days or months ago. Now, that's still very useful. However, whatever decisions were needed to be taken at the time have already been taken. So your data can only help you in this way, retroactively, to assess what's already happened. But what's already happened has already happened. How can we use data to help make decisions now, to help make decisions as things happen? This is where we look to build out actionable and preventive or predictive capabilities. And if you want to build those out, you need to be able to react in near real time or real time. So in that context, you would get the value of the historical data, which you'll always get anyway, but also you will unlock new use cases which allow you to react to events on the fly. So with that in mind, there are 2 main ways that you could process data. One is batch, which I'm sure all of you know. You have a finite period of time where you analyze a finite amount of data. And then you have stream processing, where you're processing data continuously as it comes in. So with batch processing, we process data in bulk at once, and it's large batches of data, often on a schedule. The latency is somewhere between minutes and days, depending on how fast you can get data from your source system and analyze it. Usually it's for historical data, as we mentioned, and the output is generated after the entire batch is successfully completed. With stream processing, however, you process data as it arrives continuously. And you process individual records or micro batches, and the latency goes down to seconds or milliseconds. The use cases are also more expansive. So you have real-time ETL or real-time analytics. You've got monitoring. You've got alerting. Things that you're able to do now that you're processing each record of data as it comes in. And the output of a stream processing operation happens after you process each microbatch or each record, so you can react accordingly. So to make this a bit more concrete, what are the use cases where real-time streaming is useful? So where we see this across different patterns and across different organizations is in real-time web and log analytics, for example. So if you have an e-commerce website or you have some kind of web interface where your users or your customers or your employees or students are interacting, you can analyze that clickstream data in real time and update the actions that you're taking and the events that are being processed for those users according to whatever business case you're looking to solve. And you can also analyze logs in real time so that you can make sure that the performance of that system is scaling up appropriately with the traffic. So imagine you had a Black Friday sale and you're monitoring the performance of certain marketing campaigns. You also want to make sure that your infrastructure is scaling up for the new traffic that's coming in, especially if they are time sensitive. So the second use case is transaction and event sourcing. So think of this as a single source of truth of the events that happen in your organization. So transactions that are happening in a database or a system or a POS machine or an ATM machine. This is quite useful for reacting to those events. The third use case that we see a real-time streaming platform being used for is messaging. So because you're processing data as it comes in, you can actually use a streaming platform as a message broker between different applications. So I'm sure you all know that Kafka is one of the most popular tools for that purpose, and it's also used for streaming ETL and other use cases. But passing messages between applications is one of the key use cases. Which brings us nicely to our next one, which is closely related, which is decoupled microservices. So if you have different services talking to each other, they can use Kafka or another streaming solution to broker the messages between them. And the closest parallel to what you've been doing in batch would be streaming ETL. So if you have data coming into a data warehouse or data lake and then analyzing it on a dashboard, maybe hourly or daily, you can do the same thing, but with a stream processing pipeline, you can have real-time dashboards, or you can have it down to the seconds. And finally, metrics and log aggregation. So being able to use metrics, logs, and traces to identify any kind of time-sensitive event, like a cybersecurity incident or fraud, is something that you could benefit from. So let's jump a little bit into the architecture of what this could look like. If you have a typical batch architecture, it will look something like this. This is a bit simplified. You've got your data sources on the left and then the output on the right, and in the middle you extract the data from the data sources. You do a couple of transformation steps to get it cleansed, to apply data quality, to get it modeled, and then you load that data into a downstream application. That usually takes once a day, a couple times a day, maybe once every hour. But with a streaming architecture, you can get that down to seconds or milliseconds. But the concepts are a bit different, even though the steps are the same. So first you have a source, and then you use stream ingestion technology to collect data from thousands of sources. So usually this requires more of a push approach because you're pushing an event into a streaming storage platform. In the streaming storage, you have data that is stored in order incrementally so that it can be replayed later, because the order of the events and the relationships of the events to each other are important. It's not necessarily a table like you would have in a batch. And then stream processing technologies are unique in that they process data that comes in from streaming storage in real time. And because it's continuous processing, you're not looking at a finite batch. You have to have extra functionality, such as windowing, for example, to determine what are the batches of time that you're going to choose to do your analysis in and compare them to each other and manage the event time versus the processing time, etc. A couple of functions that stream processing uniquely needs. And then finally, you output the data to a destination, which could be your real-time dashboard, or it could be back to the data lake or the data warehouse. So to give some examples of this can be used for fraud detection. So you can have data coming in, and you can analyze it on the fly and determine if this particular transaction is fraud or not. We'll see that in a second. Another is proactive risk mitigation. So let's say you're running a public campaign and you're monitoring user sentiment, and the user sentiment is trending negatively. You can take actions before it gets more negative, for example. Another is enhanced customer experience. So again, back to the Black Friday example, if you're offering dynamic, hyper-personalized offers on the fly to your customers, You could react to the browsing activity that they have and their historical data about their account and their customer lifetime value to give them a much better experience for the shopping that they're trying to do, as well as the customer service that they're receiving, so that the customer service agent or the automated bot would have the right information at the right time, not make the customer wait, get them the service that they need. So from an architecture perspective, let's talk about fraud detection. So in this example, we have data coming in, and we are producing events to Amazon MSK. Amazon MSK stands for Managed Service for Kafka, which is an Amazon service that manages the open source version of Kafka, which is the streaming storage platform in this example. The data comes in, and then it's processed by Amazon Managed Service for Apache Flink. Flink is now a very popular open source platform for managing both batch and streaming processing, actually. And in this case, it will take the real-time data from MSK, and it will send the transactions to SageMaker for real-time inference. It will then analyze those transactions, find out if they are fraud or not, and then write the result back. The result will be written to another streaming storage topic in MSK, where you would have the records, and each of them is identified as fraud or not fraud, and then that is passed on to a consuming application, which sends a notification to the fraud team so that they can take action. At the same time, you can analyze the data historically, and those events would then be sent to Redshift or OpenSearch, where they can be aggregated and then used to feed the machine learning algorithm for future fraud intelligence. So one important thing here to note is that when you go to streaming, you don't abandon batch necessarily, because you can treat batch as a subset of streaming. It's just a very slow stream. And so if you converge your architectures together, you could potentially cater to a larger number of use cases. Now, whether that makes sense for you or not, you have to analyze whether you have enough real-time processing cases in your business. But once you do, if you make the cutoff, this could be a way to save cost and reduce risk by not having two different sets of technology pipelines. You can unify them both into one streaming platform and treat everything as a stream. So this was just an example. Now let's talk about an actual case that Mimecast has gone through, the journey that their architecture went through across the years from batch to streaming. You'll hear it from the man himself, Greg.
Thank you very much. Perfect. So I'm here to talk about the journey that we've been on at Mimecast, a few of the decisions that we made along the way, why we did it, and hopefully everyone can learn from our mistakes and accelerate their own journeys. So starting off, I'm not here to sell you Mimecast, but I need to set the context. What do we do? So Mimecast is an email security, cybersecurity company. I've taken the blurb from our website. We're now pivoting to kind of human risk management, because you can protect emails, you can do everything you can, but humans are always the weakest point in the chain. So if we can protect the human, we can expand into another landscape, which is fantastic. And to summarize this all up about what we do, one of our co-founders described this perfectly. We stop bad things from happening to good organizations. And I thought that's the best summary we can do. So we talk about data, let's talk about some numbers. We process roughly 2 billion, a little bit of rounding here, but 2 billion emails every day. And we do this across 42,000 customers and millions of users. So this is the type of challenge we've got to deal with. And how I describe this about the events that flow into the data platform, there's 12 billion threat security events, which is basically coming from the email, the scanning, the detection from this. And then 85 billion other events. I kind of label this as just services at Mimecast producing data. Not this bit was what we're going to focus on, the 12 billion threat protection events. So I won't dwell on this too long, but nothing happens overnight, and there's always historical things that have been developed over time. So back in 2012, we developed an on-premise framework, which we'll talk about first, then over time how we moved to batch processing, how we moved to stream processing, and then some of the improvements we've made along the way. So I'll quickly explain this because I'm going to keep using two examples. So terminology, MTA, this is the thing that processes email. Whether you're a Google customer or an O365 Microsoft customer, Mimecast can sit as that layer around your services, providing the protection that these other companies don't. That's why we exist for that reason. And then obviously scanners, so whether there's attachments, whether there's links, whether there's content for phishing, we extract that, we scan it, then we can apply some policy. And that's how we know, is it bad or good? So, we have this data at Mimecast, we've got multiple microservices. How did we used to access our data? So back in 2012, we had the microservices logging, basically obviously the application logs. This is on a physical on-premise, so there's hundreds of thousands of servers, quite a big scale. And we developed, it's called MapBus. I had to dig through the commits, and it was definitely 2012. And this is a standard MapReduce framework. And why did we have this? So our customer support teams, engineers, PM wanted to make data-driven decisions. Thank God. And basically, it's a MapReduce style query. MapBus, centralized server, one instance, issues a request to each of the different hosts where the map job is running, if you want to call that. Basically, aggregates, brings the data back, stick in local storage, and they can do ad hoc queries or scheduled queries. Fantastic. And just to kind of say, obviously, there's a familiar SQL language. Fantastic. And just to really stress, this was from the application logs, where we could have basically key value keywords. It's a prepared structured log statement, and we could process that, and that's how we were able to achieve this. But obviously, there was some limitations of this. So it was back in 2012, we didn't design this for high availability. It could fall over. So if too many people were querying at the same time while their scheduled queries at 2 in the morning, it would definitely fall over. It crashed, gone out of memory. The data was spread across physical hosts. Physical hosts can go down for maintenance, for patching. So if you make one query at this point in time and the next point of time, you're not going to get the same results. The data was spread around. And it took a lot of engineering time and effort to maintain. One thing just to keep in mind, application logs. Why is this bad? We'll talk a bit more. But the engineer can change that log. And what about the downstream services in production? By changing a log, you have no feedback to know that you've broken a production service just by tweaking a value or changing the case. So these are things we wanted to change. So then we came up with our guiding principles about what did we want to achieve? Why did we want to move to something else? So we wanted to leverage AWS managed services for the high availability. We wanted to have the data stored centrally. Obviously, no more hosts going up and down. Our ESUP customer PMs, they can all have consistent values. Obviously, if we're using managed services, we use total cost of ownership. And something to keep in mind, Mimecast obviously has data governance restrictions, so we need to keep this data in the same region where the customer is. So the same architectures you'll see is identical across 7 different AWS regions. So with this in mind, this was our first step into AWS for batch processing. Fantastic. So left-hand side, we're still driving this from the application logs, but FluentD can scrape that special keywords, that magic string, structured data, and upload that to S3 every 15 minutes. We then have, using EMR and Spark cluster, take that hourly job of data that's being dropped. Every hour, take that data, process it, detect the schemas from the events, update that in the glue catalog, put the process data in Parquet files partitioned by date, time, service type into S3. And then customers can use a common SQL interface to achieve what they need. They can access their data, running SQL queries via Athena. You can schedule queries. Fantastic. We've solved some of them limitations, but what's the problem? Customers still, so product management, engineering support, it's not streaming. They're an hour behind. Mimecast emails don't flow in batches. They're flowing constantly. So we need to have that accurate data that's up to in real time for our support teams and PM. So a few of the limitations, just to really call these out. I mentioned application logs. That's not a schema, just to kind of say, if you really want production workloads, you need to have a defined schema so the developers know that contract ahead of time and then actively making a change. And just driving into that point again about really the developers should own that decision as opposed to a downstream team. So that batch processing, we've got that hour delay now, so we need to wait 1 hour before we can answer a customer's question about what's going wrong. Or if there's a production issue, I really don't want my teams waiting an hour to say what's the root cause. And I mentioned that we use Spark on Email to do a batch processing, but all we're doing really, in the simplest terms, is taking an input stream and transforming data. It doesn't need to be done hourly. It doesn't need distributed computing just to transform this. And then going down to, okay, this is fantastic. I mentioned about use cases. We're still not really adopting this data lake data platform across all of Mimecast to power our data. What we need, and to get there, we need a query engine that is capable of doing this. Athena is great, but currently, or back then, it had a concurrent query limit of 300 concurrent queries. If one page needs to fire 10 requests, that's only 30 users if you do 30 times 10. So underpinning all this, we needed some really solid foundations to get to our stream processing journey. And then this is where we landed. And this was back in 21. We've kind of stayed the same, or 22, stayed the same journey since. So what's changed? What's the difference before to now? So left-hand side, we still have our MTA processing email, and our scanners detecting the content. But instead of processing from logs, it's a direct integration with our client. That client is responsible for sending events directly to our data ingestion API through a load balancer. Them events, we've registered a glue schema ahead of time that's been agreed with them teams. So we can validate the schema of the events, and if they don't conform, we can reject it. So in pre-production, we can catch these breaking changes, and we have schema evolution fully compatible. So if anyone makes a change, you can always roll forwards. Hopefully, you can roll backwards. And then what the real backbone of this entire platform is MSK, obviously managed Kafka. Every event is split into this. There's multiple topics under the hood. I'm just showing it as MSK at this moment. And then we take this in a streaming fashion, so our services are deployed on ECS, takes it from a stream, writes it to S3, and at each point, we're checking against the Glue data catalog to make sure that if no one's somehow inserted events directly into Kafka, and otherwise, obviously, our streaming consumer would break. And obviously, these are still Parquet files partitioned by date, time, service type. Fantastic. So that's the data storage that's changed from before, but the batch is now real time. And then the difference on the right-hand side for querying is we now have Athena for our ad hoc queries. Fantastic. Your data science or your PM is going to run one query. But we've now introduced a query engine that can support our production use case. So we use Trino deployed in ECS, distributed computing, and we have a facade of the query API service. So no one's directly interacting with Trino. We can have an API-driven interface with the users and schedule queries. This was excellent. And then we onboarded customers, internal teams. We scaled up, we're getting towards this 12 billion events. And then we found some interesting patterns. So the first improvement we needed to do was let's start isolating some of these domains. With all good intentions, problems can happen, and some data is more important than other data, and some operations can have an impact. And how do you want to scale? So a bit more detail. How did we do it, and then some of the reasons why. So very simply, we can split the data ingestion API into multiple target groups, one for MTS scanners, other general things, and use a little snippet of Terraform. Very simple, basically send to the API path via an events for this service name that's sent in a HTTP header, service ID, so it could be MTA, it could be multiple services, and we route to the specific target group. And then corresponding, we try to isolate by domain. So if you need to scale your cluster, so the MTA might send, 8 billion events to scanners 4 billions. If you want to add more brokers to MSK, you can scale one cluster larger, and you can keep your other cluster small, so it should be more cost effective. And if you have an entirely different workflow, this will also mean you can have MSK serverless. Fantastic. We can now have domain isolation. If there's a problem with one, it doesn't impact every single service, and we can isolate different workloads. Fantastic. So a bit more on MSK. Perfect. Is to understand your traffic. So the data ingestion service itself was great. And then we found at certain times, so this is from production in EUS2, and I think this was on the 3rd of March, so it's really recent, accurate data. We can see we have scheduled queries about 2 in the morning, so there's a huge spike of data, and then there's hourly spikes throughout the day, and it's kind of email, you come to your desk at 9 in the morning, and you send an email. You go to lunch at 12 o'clock, you finish there at 5 o'clock, everyone's sending spikes. And originally, we were scaling just on CPU and memory, and that wasn't enough to support the spike in requests. So I would call out the team that did a fantastic job looking at the data, understanding these patterns. And what we could do is we could scale in anticipation. So not just auto-scaling or scheduled scaling where you go up and across. Sometimes you need to dynamically scale up enough based on a 7 days history. How much capacity do we need to add to support the spike? So we scaled up at 5 minutes to there, had a scale in period for about a cooldown period about 15, 20 minutes. And digging in production, I found something that perfectly illustrated this in the bottom. The bottom picture is the number of ECS tasks to support the data ingestion API, showing how we kind of cover the period throughout the day. Fantastic. And then some operational workloads, so kind of again trying to give a real tangible example of what we achieved. So we're using roughly 12 MSK brokers in production, 4 CPU, 16 gig of memory. And just some of the best tips, just so I'll kind of condense this for you and try on one slide. Bottom chart shows our CPU utilization throughout the day, as you can tell. So weekdays, weekends, you can kind of tell which day's the weekend, where it's less used and higher. So do try and keep your usage below 60%. This CPU usage is for the user. This is about 50% user, 10% system. So that's kind of how you can know when to scale your cluster, when to alarm, when to do this. And one thing we found that was quite tricky, or quite interesting, I should say, is if you need to add, I don't know, maybe there's a problem in your service where you can't consume data. You need to keep this data in Kafka whilst you do some other operations. When you want to increase that disk space to keep that data for longer, just be aware there is a cooldown period, so you can't change this too often because it is backed by EBS. So make sure you add enough capacity for the next 24 hours typically, just so you're not going to run into any problems. And then on this side, you can see some of the cost optimizations as well. So we moved the cluster over from Intel over to Graviton, and you don't get an instant cost saving from using Graviton, but you do get a better price performance. I'm not from marketing, it did actually give us better price performance, so we could scale down the cluster. So the act of scaling down the cluster is what's actually saved us money. And flashing this back up, because I've talked about the left-hand side, about the ingestion and MSK and the target groups in the multiple MSK clusters. Now moving towards changes on the right-hand side for how we scaled the querying. So previously you saw that there was one Trino cluster with Query API service, and you could also use Athena. But as we adopted more production workloads, we needed to add more Trino clusters without the users knowing. They shouldn't know whether we have 1 or 20. So how are we able to do this? So the config at the bottom kind of explains it quite nicely. Based on the service name from the authentication token, we can extract that with some JSON config. We just route the cluster. So Query API service has JDBC connector. It can connect to Athena, it can connect to Trino, and it can just route queries however it needs to. Fantastic. So recapping this, from the start, the journey from on-premise to batch to real-time streaming. We now have our high availability. We deployed in ECS. All the maintenance operations are abstracted from us. We deployed to multiple AZs. Fantastic. We have schema validation. We now have people making conscious decisions about the data they're sending us. Real-time ingestion. Going back to that use case of engineering support teams, the product management, and multiple engineers, we're now, and other teams of Mimecast, they can send their data to the data platform and build services and products off this in real time and not have to have any delay. We can give that feedback to customers. If there's a threat coming, we can do some analytics. We can alert customers in real time that there's a problem. And then, just to kind of really highlight, MSK is the backbone of everything we do at Mimecast. All of the streaming ingestion and data storage is pulled off that stream. And I really want to hammer this first point home. Changing the mindset at Mimecast was almost harder than the technical implementation. For people to understand their data, we went to multiple teams and said, what data do you have? We want to build some products on top of this. And we spent weeks talking about this. And now we have the shift of Developers are coming to us saying, I want to send you this data to describe this event. It's fantastic. It's been a real shift. And the Glue data catalog complements this. Using Glue, multiple service, multiple products can hook into this and all have the same query implementation. And I'll drill on this a little bit more on the next slide. The data ingestion API, you could say, just send it straight to MSK. But then some teams don't know how to use Kafka. It's nuanced, it's fantastic, but it's not magic. And I always said, well, maybe they could just use MSK, but then as soon as we did that split to have multiple clusters, we would have had to go to multiple teams to say, actually, can you change your brokers to point to these ones? So having that API has really helped. So 2 slides left, future plans, and then we'll talk about the key takeaways. Future plans for us is we have this immutable data in the data lake, but what happens if you want to change, you want to update a few fields? Well, I would absolutely love for the engineering teams to adopt Flink as a managed ingestion into an Iceberg table, so we can support basically schema evolution, mutable data, easily discover it. You have the lovely metadata to have more efficient query planning. And then the other domain that we're actively exploring right now is real-time anomaly detection. Understanding, has there been something interesting that there's a spike in mail flow, a spike in threats? Using Flink again and leveraging SageMaker, we can do time series analysis, random coforest, a clustering of logins at a certain time. This one's anomalous. We can deliver more value to customers from our stream. So I tried to do this last part in 2 sections, the shift in the mindset and the shift in technical skills. So first of all, in an ideal world, you build a platform, it's fantastic, and you don't need to worry about anything else. But realistically, you do need to know about your producer patterns and your consumer patterns. Your producers, you need to scale to their workloads. Do they send data at midnight in a huge batch? And so we talked earlier about having that streaming batch ingestion. There's ways to do this. In the future, we'll cover this. But understanding their patterns will make sure your service doesn't fall over. And this is the same for the query side. Understanding how people are going to query your data. Do they want wildcard matches? Do they want this field equals this field? Will help you prepare that data in the correct way. Having the streaming ingestion simplifies this. You just need to say, do I need a data lake, Dynamo, or Postgres? You can choose to change this. Break your service in production first. You don't want the first time this falls over, you do not want this in production. There's a few services that we've used to help us with this. So the fault injection service, you can introduce, I don't know, you can throttle the throughput, you can increase the amount of CPU load in the box, and find out where the bottleneck is. And kind of hand in hand with this is understanding what you can tolerate. If you can tolerate your service being down for a few minutes, awesome. Can you tolerate a slowness in ingestion? Maybe not, but having these agreed up front it'll save you having some difficult questions down the line. So that's the mindset. What about on the right-hand side, the actual technical side? Kafka is amazing, but it's not magic. Trust me. Please upskill the team. If you're going to use this as the heart of everything, you need to know how to address problems when they go wrong. And the other part of this is if you're a team, this is hypothetical. If your team is going to pull one event off sequentially and process that one event in sequential order, you're not going to get the throughput. You're going to spend a lot of time, your data's going to be queued up in Kafka, and you're going to complain and say, Craig, you told me this was amazing. You can tune that configuration. How many services can you scale? How many threads can you run? How many events do you need to pull for? All this will change your throughput to how much data you can ingest. That's how you can get up to, 12 billion plus 85 billion, 100 billion events from that tuning. And then finally, understanding what your service is doing under normal operation will help you understand when it's going wrong in production. Instrument your service, find out, okay, whether it's CloudWatch, whether it's Datadog, or any kind of vendor, instrument your service to find out where is it spending the time. Is it spending the time queuing queries? Is it spending the time executing some of the functionality? And going back to about breaking your service, I don't like buzzwords like SLOs or SLIs, but understanding when you're doing your performance testing, the biggest question was, what does good look like? We could spend rounds and rounds and rounds of doing performance testing. When do we stop? What's acceptable? Having that defined with product and your engineering team is exactly what you need, and you can use that for your alerting. And I think, with that, thank you very much for our Mimecast journey. I'd like to hand you back to our friends at AWS. Thanks, Matt.
Thank you, Greg, for taking over and explaining all these details. Just to give a quick recap to everyone, we know that data requirements are changing, and so are business requirements. So batch systems are not sufficient for real-time use cases. Streaming can unlock new types of value for you. I hope that the insights from Mimecast were valuable. You can take these parallels and compare them to your situation and assess whether it's right for you or not. But hopefully this has been valuable and you can keep it in mind for the future. So these are our contacts if you'd like to reach out to me if you want to build anything related to batch or to streaming, or to Greg if you want to get more details about their journey. Please, please, please complete the session survey. We love building these presentations to try and bring benefit to you. We want to make sure that it's relevant to your use case. We want to make sure that these things are connecting and that they're top of mind. So your feedback really, really helps. If you could take a few seconds to complete the session survey, we would really appreciate it. Thank you.